Okay, so we were talking about density a minute ago. Instead of writing out density, I'm going to use the symbol rho, R-H-O, Greek letter, rho, for density, mass per volume. If I wanted to calculate a density, I would need to go measure a mass, and I would need to go measure a volume. Those measurements have some element of variation attached to them. There is some natural variation in measurements that we can make as a result of just making the measurement over and over again and getting slightly different answers each time statistically, or as a result of there's only so much precision in the measuring device we have. For example, if we're going to measure a length, we might use a ruler. And there's only so much precision we have. We've got markings in millimeters and nothing smaller than that. So like the smallest measurement we can make is maybe half of a millimeter. You know, if it's between 3 and 4 millimeters, we can maybe decide whether it's closer to 3 or closer to 4 and round. But we're going to be wrong by something like a half a millimeter. So we've got that error sort of baked into using this ruler, some natural variation in a length, which could result in some natural variation in the volume. And depending what device we're using to measure the mass, there might be some natural either instrument or statistical variation associated with that measurement. Just for the sake of argument, suppose that we're measuring a mass as some particular reading, some actual reading, 17 grams, whatever it is. Plus, there's some instrument limited precision with which we can express this measurement. Suppose that we're using a digital balance and we've got, 3 decimal places, 17.000 grams. And it's going to round up to that 3rd decimal place. So if we had 17.001, that might mean it looked like 0.8. It might mean it looked like 0.6. And there's about half of a thousandth that rounds up to the measurement we had. So the variation, the error associated with reporting 17.001 is about half of that last digit, 0.005. Plus or minus, could be up, could be down, might be rounding up, might be rounding down. If we're measuring length, the length could be L0 plus or minus, we said half of a millimeter. So a millimeter would be, that's the same. Okay, fine. Well, I kind of like these to be different. Just for the sake of argument, because I want these to look different. Suppose we only had 2 decimal places from our digital scale, which means the error is half of the next place. And with our millimeters, we've got 0.001 meters, but we can go half of that. Okay, natural variation in the measurements of mass and the measurement of length. When we calculate density, there's going to be some natural variation in the result of our division because we're using variational measurements to do this calculation. how is it that the variation in our measurements of mass and length is sort of is carried through to our calculation of density? What's the variation? What variation do we expect in the calculation of density given the variation in mass and length? We're gonna draw on the calculus experience you have from the get-go here, from day one, and I'm gonna ask you to recall implicit differentiation. Let's pretend that mass and volume are functions of some other variable, such that we would need the chain rule, right? We could take the derivative of mass, but then we would need to talk about the derivative of, I don't know, the derivative with respect to something else, some other variable that mass is a function of. But we don't know what that is, so we don't explicitly say it, we implicitly suggest that such a thing exists. So we take a derivative of the left-hand side with respect to a variable that I haven't defined. And we take the derivative of the right-hand side, and this is a quotient. Who remembers the quotient rule? All right, so let's see, it's bottom times derivative of the top. And we're taking the derivative of the top with respect to a thing that we have only defined implicitly. It doesn't actually show up explicitly in our math. Minus the top times the derivative of the bottom, all divided by the bottom squared. dm, let's use dm. Let's represent the variation in our measurement of mass as the small amount by which the mass variable can change. A small differential change in mass associated with measurement variation. And let's do the same thing with the volume. Oh, wait a minute. Length, this is volume. Hold on, we gotta back up. It's not just volume. It doesn't just depend on the volume, it depends on the length. Length cubed. Okay, so now we say, okay, bottom derivative of the top minus the top times the derivative of the bottom. And to do that, we need the chain rule. 3 comes down, and then L squared dl, because we're pretending that L is a function of some other variable. Then divide by the bottom squared. Okay, now we're talking. So now again, let's represent the variation error in mass as dm and the variation error in length as dl. And these LM variables, those are the basic measurement. That's L0, M0, so we have our primary measurement. The length and the mass. But we could be wrong. There could be some small change in the mass, dm, some small change in the length, dl. How did those changes result in a small change in the density? This way. We can use implicit differentiation. to estimate the small change in the density as a result of the small changes in the mass and the length. We'll practice this on Monday in the analysis you perform about our first lab. So there's that, and we're ready for the next segment.